So the last bit that we want to look at is some relationships that exist between the binomial coefficients. It all comes from our binomial theorem, which in shorthand notation I've written there with the sum, general term of course being nck x to the power of k. Expanded out, it would look something like that. So find the value of nck, sum of going from 1 to n. So how do we approach this sort of thing? Well, these sorts of questions all start with the binomial theorem. So I write it down. I go, well, what's different about these two things? Anything obvious that we spot that is different between what I want to find and what I got? Anyone notice anything? It might seem really obvious. Right, the x is not there. How can we make the x go away? If instead of writing x there, what could I put instead of x? 1. Because 1 to the power of anything would be 1. So let's do that. We'll let x equal 1. So the left-hand side will become 1 plus 1 to the power of n. The right-hand side is nck 1 to the power of k. So we've almost got what we want. The other difference. Yeah, so this one's going from 0 to n. The one we want is 1 to n. So all I've got to do is subtract the term where k equals 0. Well, we know k equals 0, sub it in, we'll get nc0. We also know nc0 is always equal to 1, regardless of what n is. So if I move that to the other side, I get a result. So nck, starting at 1 going to n, will always be 2 to the power of n minus 1. That does bring up another classic result. If I go back a few steps, this one here, 2 to the power of n. In any row of Pascal's triangle, all the terms will add up to be 2 to the power of n. So that's a nice, neat little relationship, which sometimes they ask us to prove by itself. In this case, I went from 1 to n. Okay, what about if I just want to add up all the odd ones? So again, let's start with our binomial theorem. There it is expanded out. That might make it more useful. So I want NC0, NC2, NC4, all the even ones to go away. I want to be left with the odd ones. We just saw that if we let x equals 1, all of those will add up to be 2 to the power of n. Okay. I want to get rid of the even ones. So what I now do is substitute a different number in. If I substitute in -1, then when I go x to the power of something, it's going to alternate between plus and minus, plus and minus, plus and minus, depending on whether it's an odd power or an even power. Well, on the left-hand side, they equal 0. So when they alternate between plus, minus, plus, minus, plus, minus, they add up to be 0. Well, what I've now got is simultaneous equations. I want to be left with which ones were we going for? The odd ones. So if I add or subtract, what do we got to do for this one? If I subtract, that'll get rid of all of the even ones, because we'll get NC0 minus NC0, NC2 minus NC2, and so on. But I'll be left with 2 lots of all the odd ones. Well, if I divide both sides by 2, there's the result. All the odd ones add up to be 2 to the power of n minus 1. It actually means all the even ones do as well. Because what would have ended up happening if I went for evens, I would have added the 2 equations together. And so I still would have got 0 plus 2 to the power of n. I still would have got 2 to the power of n, but now I'd be left with all the even ones. K, NCK. There is our binomial theorem. Well, what's different? Again, let's have a look at what we got and what we're trying to get. What do we spot?
Instead of the variable x.
Yes. We have k instead of x. How on earth can I get k there as one of the coefficients? Right, so something we've done recently, and that is differentiate. Remember, whenever we differentiated the polynomial, we got the power and put that to the front, and it became a coefficient. So if I was to differentiate both sides of these, so the left-hand side will become, well, bring down the power n, lower the power n minus 1, diff the inside, well, the inside diff will just be 1. But in our sum notation, every term would be bringing k down to the front. All right, well, we're close. Mind you, there's still a difference there. How am I going to get rid of that x? Same as we did before. We'll let x equal 1. So if we let x equal 1 in this one, we've got 0 to n. Again, we've got the same problem. I only want 1 to n. Mind you, in this case, it's not going to make a lot of difference when you think about it. Because if I sub 0 into my general term, I'm going to get 0 times nc0, which is obviously 0. So we'll get that the sum of k nck is n times 2 to the power of n minus 1. So all these little playing around with the coefficients just involve, start with the binomial theorem, and then just have a look, well, what's different? How can I make this binomial theorem into what they're asking me? This is probably one of the more trickier ones of them all. By equating the coefficients of x to the power of n on both sides of this expression, we're going to show this wonderful relationship. So that the sum of nck all squared is 2n factorial over n factorial squared. Okay. Remember, there's our binomial theorem, which, if I expand it out, would be that. So, all right, they've given me a hint. They've said, have a look at the coefficients of x to the power of n. So I'm going to look at the coefficients of x to the power of n in 1 plus x to the power of n, so that expression there, times by itself. Okay. I want to pull out all the terms that will give me an answer of x to the power of n. So let's start at the front. nc0. Well, that's going to have to multiply by the ncn x to the n. So I'll get nc0, ncn x to the n. nc1x, well, that's going to have to multiply by the x to the n minus 1. So I get nc1x times ncn minus 1 x to the n minus 1. That'll become x to the power of n. nc2x squared, that'll be times the x to the n minus 2. And I'll keep going and keep going and keep going until I get to the end, and I'll get ncn x to the n times nc0. So the coefficient, I'm not worried about the x to the n, I just want the coefficient. I end up with nc0 times ncn, nc1 times ncn minus 1, nc2 times ncn minus 2, and so on and so on and so on and so on, until I got to the very end, which was ncn nc0. But, using a Pascal's triangle relationship there, we know it's symmetric. So nck is the same as ncn minus k. In other words, nc0 is in fact the same as ncn. And nc1 is the same as ncn minus 1. And so on and so on and so on, all the way down. So I could rewrite all those as nc0 squared plus nc1 squared plus nc2 squared up to ncn all squared. In other words, the sum from k equals 0 to n of nck squared. That was one half of what we're trying to show. But it's said to look at x to the power of n of both sides. So now let's have a look at 1 plus x to the power of 2n. This one's going to be a little bit easier because this is just a straight expansion. It's just that the power is 2n instead of being n. So we'll have 2nc0 plus 2nc1x plus 2nc2x squared and so on. Somewhere in the middle, there'd be a term 2ncn x to the power of n. And it'll be the only term that has x to the power of n. So on the right-hand side, that's what we get, 2ncn. All right. But those two things have to be equal. They were just two different ways of coming up with x to the power of n. So we know they're the same thing, so therefore, that's close. Still not quite what they want us to show. The left-hand side's fine, nck squared, but the right-hand side, they had broken that back into factorial notation. So that would be 2n factorial, so my top's okay. On the bottom would be n factorial. Two numbers have to add together, in this case to get 2n. So it must be times n factorial, which is n factorial squared. All right, so as I say, left the best to last there. That's probably one of the more trickier ones where you've got to compare the coefficients on both sides. So 15D, there's a handful for you to play with